Welcome to The Explainer. Today, we're cutting right through the hype to fundamentally understand the history, the mechanics, and the actual reality of artificial intelligence. If you've been following the space at all, you know AI is literally everywhere right now, but the core concepts driving it are so often buried under a mountain of heavy jargon. Well, today, we're going to change that.
So, can a machine actually think? It's a huge question, right? And it's not just some modern tech obsession either. It's really a foundational curiosity that's driven decades of intense mathematical and engineering pursuit. Long before we had the raw computing power to actually test it out, this idea lived purely in the realm of philosophy and human ambition.
Okay, here's our roadmap for today. We'll be looking at the dream of machines, booms in AI winters, how AI actually learns, real-world AI applications, and finally, the ethical crossroads.
Section 1. The Dream of Machines. You know, long before microchips or digital data were even a glint in anyone's eye, the concept of artificial beings was already deeply rooted in human imagination. We're talking ancient Greek myths of mechanical men, like the bronze giant Talos, or medieval alchemical legends. It really shows us that this desire to create intelligence outside of ourselves has always been part of the human story, which eventually blossomed into a serious academic discipline. And the path to modern AI has essentially been a massive, multi-generational relay race. Just look at some of these pivotal moments. In 1950, Alan Turing proposes his famous test. By 56, the field is officially founded at Dartmouth. Then, we hit a serious wall in 74 with the first AI winter. But look at the incredible acceleration in the 2010s. We see a massive boom in 2012 when GPUs finally accelerated deep learning, followed closely by the breakthrough transformer architecture in 2017. So definitely not an overnight success, but a really long, complex timeline of theoretical breakthroughs and huge technological leaps. Which brings us to Section 2, Booms and AI Winters. Progress in this space was never a straight line up. The field experienced what researchers call AI winters. Basically, these were harsh periods of severe funding loss and deep disappointment that inevitably followed cycles of extreme optimism. Why did it happen? Well, early researchers slammed into what's known as a combinatorial explosion. Imagine trying to solve a puzzle where every single new piece adds 1,000 more pieces. As their problems grew, the algorithms became exponentially slower. The computing power just literally wasn't there yet, and that led to devastating funding droughts through the 70s and 80s. Now, there is a really crucial distinction we need to make here. On one hand, we have narrow AI. These are highly specialized systems built to do things like beat a grandmaster at chess, translate languages, or curate your movie recommendations. We've completely nailed this. On the other hand, we have artificial general intelligence, or AGI. This is the hypothetical ultimate goal, a system with human-level cognitive breadth that can seamlessly transfer its learning across virtually any task you throw at it. Make no mistake, we are still firmly in the era of narrow AI, even though companies are sprinting toward AGI. Moving on to Section 3, how AI actually learns. So how did we actually break out of those AI winters in the 2010s? Well, instead of that old-school step-by-step programming, deep learning leans into biological metaphors. An artificial neural network works kind of like a massive game of telephone inside a computer. Raw data passes through an input layer, then bounces through multiple hidden layers of nodes until a distinct pattern is recognized and spat out. When a network has multiple hidden layers, we call it deep learning. It's essentially just advanced pattern recognition mimicking the synapses of a biological brain. And when it comes to training these networks, it largely splits into two main methods. Supervised learning is kind of like using flashcards. We feed the machine millions of explicitly labeled images, literally telling it, hey, this is a cat, over and over until it learns the pattern. Unsupervised learning, though, is more like dropping the AI into a messy room and asking it to organize. It's let loose on massive streams of raw, unlabeled data to find its own hidden structures and groupings without us telling it what to look for at all. But how does it actually make a choice? When it comes to automated decision-making, a rational AI agent generally follows three logical steps. First, it perceives its environment using whatever sensors it has. Second, it calculates the expected utility. Basically, it's crunching the math on all possible outcomes and assigning a probability to each based on what it's trying to achieve. Finally, it acts to maximize that defined goal. It's essentially just making its absolute best mathematical guess in an incredibly unpredictable world. Section 4, Real-World AI Applications. So where exactly does all this complex math and computational power live today? Honestly, everywhere you look. It's the recommendation algorithm curating your YouTube and Netflix habits, the software actively driving autonomous cars and drones, and the tools providing clinical decision support right now in your local hospital. And of course, natural language processing and generative AI have handed us chatbots capable of casually passing the bar exam, alongside tools that generate breathtaking art and literally write software code. AI is definitely no longer a science project. It is the fundamental infrastructure of our daily lives. And that brings us to Section 5, the ethical crossroads. Because of this sudden massive integration, we're suddenly face to face with some very serious risks. These systems easily inherit human biases straight from their training data, which leads to unfair, real-world outcomes in critical areas like hiring or lending. We're actively grappling with a tidal wave of misinformation fueled by highly realistic deepfakes, incredibly complex copyright battles over the training data, the harsh economic reality of technological unemployment, and yeah, even long-term existential debates about what happens if these systems become vastly smarter than us.
And because just a handful of massive tech giants currently control the necessary data centers and that crucial raw compute power, the stakes couldn't be higher. Governments and researchers all over the world are locked in this intense debate. How do we possibly build regulatory frameworks that ensure transparency, safety, and accountability without totally suffocating innovation? It's an incredibly delicate balancing act, and it's playing out on the global stage right as we speak.
It's pretty wild to look back at 1950 when Alan Turing set out this seemingly simple benchmark. If a machine could carry on a conversation that was indistinguishable from a human, it was entirely reasonable to say that the machine was thinking. Over 70 years later, what used to be a fun philosophical thought experiment is now literally chatting with us on our smartphones, writing complex code, and acing graduate-level exams. Which leaves us with this one massive question. As these artificial systems reach unprecedented levels of capability, how will we ensure these incredibly powerful tools remain aligned with our own values and our collective future? I'll leave you to ponder that vital question as we navigate this wild, new technological era. Thank you so much for joining me for this explainer. Keep learning, keep asking questions, and I'll catch you next time.